Alright, hey everyone. In this video, I'm going to be going through how to solve all the problems in Exam 1 from 2018. And these include problems that we haven't covered yet in class, but with the exam a week away, I thought it'd be nice to cover as much as we can. So without further ado, let's dive in. Numbers 1 through 7, citric acid cycle, we haven't covered yet, so I'll explain the best I can with what we know. So number 1 says, which step in the citric acid cycle, as shown here, is most analogous to the conversion of G3P to 1,3-bisphosphoglycerate, which happens in the citric air in glycolysis. So the enzyme that is responsible for this reaction is called G3P dehydrogenase. And as we know in most of biochemistry, the names of enzymes give us a good hint about what they're doing. So that's one way we can go about answering this question. Because this is called G3P dehydrogenase, what it's doing is a dehydrogenation. It is a dehydrogenase in its function. And when we learn the names for these enzymes, what we're going to find, one, which is reaction 0 here, is the pyruvate dehydrogenase complex. And that is one that is similar or analogous to what's happening here. Another one that we will learn about is isocitrate dehydrogenase, which is the enzyme involved in step 4. And then we'll also learn about alpha ketoglutarate dehydrogenase, which is in step 5 here. And those are all dehydrogenases, and they are fairly similar to what happens in this reaction from glycolysis. Another thing we could look at that we probably haven't seen yet and is not here, but if you've labeled this, once we get to it, will help. You will see for all of these, NAD is involved. We put in NAD plus and we get out NADH. So that's another thing you could look at that would indicate this answer might be the right one. Number 2, alpha keto acids. Which ones are alpha keto acids? By an organic chemistry definition, if you Google what is an alpha keto acid, it's a compound that has a ketone group right next to a carboxyl group. And the way that I learn it, maybe a more practical definition, it's all the molecules where you replaced the amino acids amino group, the NH2 or NH3, replace that with a ketone group, and that gives you an alpha keto acid. Not all alpha keto acids turn into amino acids, theoretically, but all amino acids with their NH3 group replaced with a ketone, all of those are going to be alpha keto acids by definition. So we've learned about one of these already, and that was pyruvate. We know if we switch this O to single bond NH3, that gives us alanine. So if the answer choice A was an option, I would say that one is a good option. Another one, if we go through and look and see right here, this might look real familiar as glutamate. And here's the side chain. Here's the carboxyl, here's the amino terminus. And that is F, which is choice B. And if we go through, you might think this one does, but notice here it doesn't have the carboxyl group. It's been replaced with acetyl-CoA, or just CoA, actually. So that's not an amino acid, so it's not an alpha keto acid. Now here, this should look a whole lot like aspartate, with this being the side chain, and right here, the part we replace. And what happens is a transamination. That's the kind of reaction that goes from an alpha keto acid to an amino acid. And we call those, there we go. So our answers for this would be answer choice E and answer choice B, which corresponds to F. Okay. So this is just some basic previous chemistry that hopefully you're well aware of. Number 3, intermediate C, which is citrate here, consists of what kind of alcohol or yada yada. So we do have an alcohol here, right? If it was a double bond O, this would be a ketone, right? This would be a ketose as a carbohydrate. So as an alcohol, we see that here it's a 1, 2, 3, a tertiary alcohol, because there are 3 carbons attached to the carbon with the OH group. And so that's 1, 2, 3 carbons. If there was only 1 or 2, it would be primary or secondary, respectively. For number 4, glyoxylate cycle, sometimes it's also called the glyoxylate shunt, is something that we've not covered in class, but we'll learn about it soon. It's more to do with plants, but here, in my opinion, here involved with tuberculosis, and this cycle allows for TB to persist in latent granulomas for years. And so we're going to learn about this, where it happens, and the step that it bypasses is number 4 right here. And then it goes off to the glyoxylate shunt, but I like to visualize in the middle here. What helps me remember where it is that, remember here we talked about how NAD is going to be required, forming NADH. All these other steps, sure, up here we need acetyl-CoA to form, we need coenzyme A to form acetyl-CoA from pyruvate, but that's not really like an energy token necessarily. So all of these can happen until step 4, like what's called step 4 here, which forms alpha-ketoglutarate from isocitrate, and that step requires stuff. So in my brain, I'm like, oh, if you don't have the stuff you require, you can go off on an alternative, less efficient pathway. I don't know if that's the fundamental truth of why it happens, but it helps me remember. Also, just write it in on your thing, and then you know for sure. That's a good idea too. Arsenite inhibits the following steps. So arsenite, we've learned about this from glycolysis, and we remember it was inhibiting G3P dehydrogenase. It inhibited the formation of 1,3-BPG. It passed over this guy. Arsenite did. So maybe are there some other dehydrogenases that it might be involved in skipping over? For example, pyruvate dehydrogenase, as well as the one we have down here, alpha-ketoglutarate dehydrogenase. These two are both very similar in mechanism. They're both adding the CoA, taking off a carboxyl. So those two are real similar. They are inhibited by arsenite, of the ones shown here. Number 6, this molecule is flipped in the active site for stereospecific hydration reaction. This one right here, I'm pretty sure it's called cis-aconitate. A lot of figures I see with citric acid cycle don't include it. You could almost think of it as not a transition state, but maybe a less stable intermediate that goes through. A lot of times we see from citrate to isocitrate, and these two are both done by aconitase, the enzyme. There we go, and it's really important for stereospecificity. That's one way you can remember that the answer choice is D here. Another way to think about it, it's a hydration reaction, which is going to be you take either a double bond or a pi bond, and you hydrate it. You add an OH to one side and an H to the other. The only place we have a carbon-carbon double bond is right here, as well as right here. But notice this one, there's no stereospecificity to be had. There's no R or L options, where here there is stereospecificity. So the answer choice is D, and that's a couple ways we can maybe remember it. Number 7, this is going to be carbon tracing through citric acid cycle. I'm sure we'll get more practice with this, but we can go ahead and walk through how to solve this one now. So when cell extract containing all the stuff we need for glycolysis and citric acid cycle is incubated aerobically, so it's working with glucose labeled with carbon 14 at carbon atom 4 and 5, what fraction of the original label will remain an oxaloacetate after one turn of the citric acid cycle? Assume all labels enter the cycle in the first citrate synthase step. Okay, cool. So we'll chat about that in a second. I'm going to go ahead and show a new version, so it's less messy. Here we have the citric acid cycle again, and here we have the glycolysis pathway. All right, so we are told that glucose is labeled at carbons 4 and 5. I think now is a good time. You can go ahead and pause the video if you'd like to, find carbon 4 and 5, and find out where it'll be in pyruvate. So first, what we had to do is find out where carbons 4 and 5 are. So here's 1, 2, 3, carbon 4 is here, carbon 5 is here. And now now trace it if you haven't yet. All right, so going through 4, 5, 5, 4, 4, 5. Brighter, there we go. All right, notice how it's away from the phosphates. It'd be like right there and there, there and there. It could be there or there, there and there, here, 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 and here. Perfect. Okay, so we find it's in 2 spots, which makes total sense, right? It could be here or it could be here. Now, one thing we remember is this whole section here happens twice, right? This happens twice. One of those is going to be tagged. If we cut this one in half, one will be tagged, one won't be tagged. Now, what's said at the end here is that assume all label enters in the first citrate. So that just means the one that didn't have the label, let's just not think about it, right? Because obviously one will have no label, but don't think about that in your calculations here. So we're going to see label right here and right here in pyruvate. Now we know pyruvate is going to be starting and then ends up in the citric acid cycle. So this pyruvate should be the same as this pyruvate here. So let's figure out where the tag is, just transferring between the different styles of writing. One is obviously the middle carbon, as we can see, one of the ketone. The other one is the carboxyl group, which here is written like that. I'll put it off to the side. Now, here we have an issue. Here's pyruvate with 1, 2, 3 carbons, but after the pyruvate dehydrogenase complex, we form acetyl-CoA. Acetyl-CoA only has 2 carbons, but we had 3. Now the question is, which carbon did we lose? If you guessed the COO, you're right. And what did it leave as? It left as CO2. So this carbon that was tagged is now gone. And specifically that was carbon 4, in case you're wondering. That carbon is gone. So half of our tag that we put in at the beginning, it's not there anymore. After the 0th step, before we even got into the citric acid cycle. But there is still some, and we have to see how much, see if it makes it all the way to the end. And where is it going to end up? Let's read the question again. What fraction of the original label will remain in oxaloacetate after one turn or one pass through the citric acid cycle? So oxaloacetate is this one K right here. So once it reaches there, how much is going to be left? Well, we've already lost half of it in this first step, so we're not off to a good start. But we do know that the carbon with the oxygen on it, which is going to be the one right here, it's still tagged. Now, where does this one go? So if we look over here on citrate, where I'm going to see it end up is right here. Because I see that the carbon, the one with the CH3 will become one with the CH2. Okay, and then I can just follow this around. Notice things are happening. There's a isomerization occurring, but everything's still the same. Notice here we lost a CO2. See, the one that was here is now gone. There's 1, 2, 3, 4, 5 versus 1, 2, 3, 4, 5, 6. So we lost a CO2 there, but that was not the one we tagged, so we're good. The one that's tagged is still right here. We just lost another carbon in step 5. At the bottom one, and acetyl-CoA. Remember, this one is very similar to pyruvate dehydrogenase. So now our tag is still at the top. Here it's at the top, but notice this molecule is symmetrical. So how do you know if we turned it over? It could be there. But if we turn this one over, it's obviously different, right? But this one, because it's symmetrical, it could be here or here. The same is true for the next couple steps. And once we make it here, it could be the top or the bottom that it's at. But this question doesn't ask about where is the tag, it just asks how much is left. And let's say at the beginning in this glucose, we started with a total of 1, right? Now, once we got to pyruvate, we still have a total of 1 because we're only looking at the 1/2. But in this step here, pyruvate dehydrogenase, remember we lost half of it. Like all of it that was on, in this case it would have been carbon 4, is leaving as carbon dioxide. So half of it won't end up in oxaloacetate. But none of the other carbons that were tagged were lost. So all the others that remain are going to be in oxaloacetate. And oxaloacetate, we can write as OAA as a short. But half of it will be on one carbon, and half of it we would assume would be on another. Right? So if you ask per carbon how much of the relative, it'd be 0.25 after one round. But it asks total, and that's 0.5. So that's how we solve that one. One thing to note is this is a cycle. It can happen more than once. So we could continue following around. This carbon right here, for example, would be right here, and then it'd be here, and then here, and then here, but then it would be right here. It would leave. We could also follow this top carbon. It's here, but it won't be here anymore. Now I think of it as like falling over, getting squished. So now it's over to the side. And this one, we'll notice, leaves in step 4. So we can trace where the carbons go. So after 2 rounds, how much would be left? 0, based on what we were given there. So I hope that was super helpful, or a little bit helpful. And yeah, that's all I have for this video.